Good morning, everyone. My name is Deanne Coppejans, and I'll be talking about whether the fast blue optical transients, or FBOTs, are potential probes of intermediate mass black holes. So firstly, what are fast blue optical transients, or FBOTs? These are transients that rise in the optical on timescales of only a few days. They're very luminous, greater than 10 to the 42 ergs per second in optical at peak, and this luminosity can rival even the superluminous supernovae. At peak, they also show blue and featureless continua. You probably have heard of the most famous one of this class, 80-2018 Cal. So what are they? Well, at the moment, we don't know for sure, and it looks like they might be a diverse class of objects as well. This is just a sample of the models out there for them, but they generally fall into two categories. The one is interaction models. This is where a supernova goes off in a very dense environment, and the FBOT is then the supernova shockwave breaking out of this dense shell of material surrounding it, or alternatively, the cooling envelope emission from this material will form a radially extended star. The second class of models invoke energy input from a compact object, such as a magnetar or a black hole. And in the case of the most luminous FBOTs that we've observed at multiple wavelengths, there's clear evidence that there is a compact object driving emission from these FBOTs. Now, examples of what I mean include supernovae or failed supernova, where the core of the star has collapsed to form a magnetar that can help power the transient via spin down, or else collapse to a black hole that helps power the transient via accretion. Now, the reason I'm here talking to you today is one of the models for FBOTs are tidal disruption events around intermediate mass black holes. So there have been 3 FBOTs detected at X-ray wavelengths to date, and they're shown here in red and orange stars. Their X-ray luminosity is a function of time, and I've shown a few other classes of transients for comparison. So the key takeaways here are that the X-ray emission from these luminous FBOTs is very bright, comparable to those of the gamma ray burst, and it declines very steeply, faster than any other class of transient, in fact. Now, in 2018 Cal, the X-ray emission also showed evidence that there is a central engine, or a compact object powering the transient. In the top left, you'll see a light curve taken a few days post-discovery, and you'll see variable emission on timescales of days. If you look at the lower right plot, just look at the black points, you'll see that the X-ray emission remained variable up to a few tens of days post-explosion. And it also showed an extraordinarily steep decay rate of T to the -4. The full X-ray SCD also shows some very interesting components. So if you just look at this first panel here, this is the X-ray spectrum taken about 8 days post-discovery. And you'll see that at above 15 keV, there's a hard X-ray component, and about 8 keV, there's an emission line. But moving forward in time to 10 days, the contribution from this hard X-ray component has decreased. And at 16 days and onwards, it's completely disappeared. So there's this evolving hard X-ray component and this 8 keV emission line. This is reminiscent of Compton hump spectra. Now, these 3 pieces of information, the variability timescales, the decay rate, and this evolving spectrum, show that there is a central engine involved in 18 Cal. Now, there have been 4 FBOTs detected at radio wavelengths. Again, this is in comparison to the few dozen that are known at optical wavelengths. And here I've shown their radio luminosities as a function of time since discovery in comparison to other classes of transients again. And again, the takeaway here is that the radio emission is very bright at peak, comparable even to gamma ray bursts and Jetta TDEs. and the decay rate is extraordinarily steep as well, at T to the minus 2.7 for CSS 161010. The interesting thing too was that the ejecta from CSS 161010 and the koala were mildly relativistic. So this directly indicates that there's a compact object driving the outflows from these objects. And interestingly, with these unique optical properties and these mildly relativistic outflows, these are a new class of transient that have recently been discovered now. So they're exciting from a number of different perspectives. But getting back to the central story, here I have plotted the outflow velocity at very high, the outflow energy at very high velocities versus the outflow velocity. So if you're not familiar with this type of plot, what you're looking at here is in the lower left corner, you've got transients where most of the energy is carried in the slow moving ejector. So we're considering normal supernovae. As we move to faster velocities and higher energies, we approach the top right-hand corner where you've got things like gamma ray bursts, where you've got a lot of energy and it's all carried in the fastest moving material. So moving to lower left to the upper right, you're becoming more relativistic. And these two FBOTs, the koala and CSS 161010, are intermediate between these two classes of object, and they indeed show energies that are comparable to the gamma ray bursts. So they're in a very interesting area of phase space. Just making the story more interesting, CSS 161010 was actually hydrogen rich. This is the first hydrogen rich transient with a relativistic outflow. Now, there were theoretical reasons to expect that hydrogen-rich progenitors can't launch mildly relativistic outflows, so this was a very exciting finding. Now, what are the host galaxies of these luminous FBOTs like? Well, in this top panel here, I've plotted the star formation rate of the host galaxy versus the mass of the host galaxy. And again, the luminous FBOTs are shown as red stars. And you see that they are all in dwarf galaxies. In fact, CSS 161010 was in a tiny little host that was only 10 to the 7 solar masses. So they all prefer host galaxies so far. So if these luminous FBOTs are tidal disruption events, then if you extend the black hole mass scaling relation down to host of 10 to the 7 to 10 to the 9 solar masses, then you derive a black hole mass of 10 to the 3 to 10 to the 4 solar masses. In other words, if these are TDEs, then there must be TDEs on intermediate mass black holes. The caveat is that it's not clear what the black hole population in these tiny hosts are like, and it's not clear if we can actually extend the black hole mass scaling relation down to galaxies of this size. So just to give you the broad properties of the most luminous FBOTs, I'm just referring to those that peak at with optical luminosities greater than 10 to the 44 ergs per second. They have short rise timescales of a few days. Their peak luminosities at opticals 10 to the 44 ergs per second or greater, well, approximately 10 to the 44 ergs per second. They have specific radioluminosities of 10 to the 28 to 10 to the 30 ergs per second, X-ray luminosities of 10 to the 33 ergs per second. We found a variety of outflow velocities with the fastest material moving at 0.1 to about 0.6 C. That is either hydrogen rich or hydrogen poor in individual objects. We know that they can launch mildly relativistic and hydrogen-rich outflows, and they don't show any highly collimated gamma ray burst-like jets. They are powered by compact objects, and we know that they have very dense surrounding environments. So from radio observations, we detect environments that are compatible with a mass loss rate of 10 to the minus 4 to 10 to the minus 3 solar masses per year if you assume 1,000 kilometer per second wind of the progenitor system. They're also very rare. So their rates are less than 0.4 to 0.8% of the core collapse supernova rate in the nearby galaxy. Beg your pardon, in the nearby environment. And their hosts are dwarf galaxies. So are these luminous FBOTs TDEs on intermediate mass black holes? Well, the general argument is that for a 10 to the 3 to 10 to the 4 solar mass black hole, the fallback timescale would be on the order of a few days for a low mass main sequence star. And this short rise time is comparable to the 4-day rise time of FBOTs if the circularization of the fallback is efficient. They also have blue featureless spectrum at their peak, and they're powered by compact objects, and this is reminiscent of tidal disruption events. So I'm going to look at the 3 systems that we have multi-wavelength observations of now and see if they're TDEs. Let's look at 2018 Cal first. This has been proposed to be a TDE of an intermediate mass black hole. But the problem is you would need to be accreting at about 10 to 100 times the Eddington luminosity. More difficult to explain though is the dense surrounding medium. So to explain the density that we derive from radio observations, you would need a mass loss rate of about 10 to 100 times the Eddington accretion rate, or you alternatively would need an accretion rate of about 10 to minus 4 solar masses per year. But this object was not in the nucleus of the galaxy, it was offset. So it's hard to explain these really dense environments in its location. So based on our modeling of the full radio through to hard X-ray data set, we rather favor scenarios invoking supernova explosions, formations of compact objects rather than a TDE. Looking at CSS 161010, so if this is a TDE, it would have a host that is at least 10 times smaller than any confirmed TDE host. But the host is a dwarf galaxy, but it doesn't show post-starburst features. And the luminosity would need to be at about 10 to the power 3 times the Eddington luminosity. I will say that there are very large uncertainties on that number, however. So in this object, we couldn't rule out a TDE. We do favor rather a rare path of stellar explosion from a massive hydrogen-rich progenitor. In the koala, they found that the optical emission must come from shock breakout of a dense shell of material surrounding the transient. And they again couldn't rule out a TDE and also favored a rare path of stellar explosion. So the jury is still out on whether these luminous FBOTs can be intermediate mass black hole tidal disruption events, but the short rise timescales and the blue featureless spectra at peak, the dwarf host galaxies and compact object powered outflows have inspired this model. Now, if some FBOTs are TDEs on intermediate mass black holes, then they're a way to identify intermediate mass black holes and constrain potential intermediate mass black hole rates. They also would provide a means to study accretion and outflow physics of TDEs in a completely different regime, and they would be a way to probe the black hole properties of dwarf galaxies. To conclusively establish whether FBOTs are intermediate mass black hole TDEs, we need more multi-wavelength observations of the most luminous FBOTs, and we're busy trying to find more of these rapidly evolving transients at the moment. We also need to understand the circularization timescales, the accretion flows, and other observational properties expected from TDEs on intermediate mass black holes. Thank you.